Well, this is a screencast to introduce you to Chapter 2 for Physics 231C. Chapter 2 is called Motion in One Dimension. It has several sections. Section 1 is position and displacement. Section 2 is velocity. Section 3 is acceleration. 4 is one-dimensional motion with constant acceleration. And then 5 is free fall. So we start with a kind of definition of some terms. The subject here is called kinematics. Do you know that word? Kinematics is the description of motion using mathematics. The first part of Physics 231C is called mechanics. That's the theory of force and motion. So this branch of physics, really the oldest part of physics, seeks to determine how forces affect the motion of the objects on which the forces act. And kinematics is an important part of mechanics. So kinematics is the description of motion using mathematics. Physics is a mathematical subject, and it always has been since the very beginnings of science of physics. And it's quantitative. So physics is concerned with equations that describe some phenomenon. And in the case of motion, we need several mathematical techniques to describe motion in a mathematical way and in a quantitative way. Some of the mathematical techniques that are necessary are coordinates. We use coordinates to specify the position of an object as it's moving around. And vectors, well, this chapter is in one dimension, so the vectors aren't so important in one dimension, but in 2 or 3 dimensions, the position is described by a vector from some origin in space, some fixed point, to the position of the object. And functions. Let's go to motion in one dimension. The position will be given by a coordinate, and the position will be changing in time as the object moves around. So the coordinate will be a function of time. So in this chapter 2, we're considering motion in one dimension only. You can think of a car moving on a straight road, or you could think of an object moving in Earth's gravity, moving straight up or straight down in Earth's gravity. Come to that in section 5. Or just in a mathematical form, you could consider this to be motion along a line. All right, so the first section is called position and displacement. We have this object, like this red box, moving along a line. And we'll think of this line as a number line in order to locate the position of the object. So we have along this line a fixed point, which is called the origin, and the position along the line is a number. We call that the coordinate. So we'll call the moving object a particle just for terminology. When I say a particle, what I mean is a small object. Something that's small, and I don't really care if it's rotating. I'm just looking at the position of the center of the object. So what I mean by position is the position of the center of mass point. Just think of it as a small object, there's a position, that's the position I'm talking about. Now, as the object moves along the line, its coordinate will be changing. So I'll call the coordinate x, and x will be a function of time t. T is time. Now, there's some jargon which is sort of important. There are two terms, displacement and distance. They are similar but different. The coordinate, x, is the displacement from the fixed point, O, the origin. Now, the displacement can be positive or it could be negative. This shows a position which is positive displacement. It's to the right of the origin. I define the direction of the line segment, or of the number line, as being to the right. Then the positive numbers are to the right of the origin. I can think of the origin as the point 0. So this position would be a positive displacement from the origin. So the coordinate would be positive. But if the object were over here, that's a negative displacement. It's to the left of the 0 point. It's in the negative region. So the coordinate, that's x, is the displacement from the origin. Now, what's the distance? The distance is the magnitude of x, or the absolute value. So the distance from the origin is the absolute value of x. Now, displacement could be positive or negative. So this is a positive displacement, and it's a positive distance. But this is a negative displacement. It's displaced to the left of the origin in the negative direction. I specify the right word to be the positive direction. So this is a negative displacement. And the distance from the origin is the absolute value of that displacement. So distance is always positive, but displacement can be positive or negative, because there's a direction associated with this line, which I indicate by this arrow. Now, for one dimension, we use the words position and coordinate interchangeably. So when I say coordinate, what I mean is position. Or when I say position, what I mean is coordinate. When we come to 2 dimensions, or even generalizing to 3 dimensions, it's more complicated, because then there's a direction. And so position has to be a vector. But in 1 dimension, position and coordinate mean the same thing. Now the position depends on time, because the object is moving around. So x of t is a function in which time is the independent variable and coordinate x is the dependent variable. And they'll both have to have units. We studied measurements back in chapter 1. The unit for time will be seconds. That will be the standard unit. Now, we might sometimes use minutes or hours, but there's always a way to convert between minutes, hours, any other unit of time into seconds. So we'll choose as the standard unit of time seconds. And the standard unit of position is meters. It's the distance from the origin to the position of the object, or the negative of that distance if the object is to the left of the origin. So again, we could use miles, we could use feet, we could use inches. There are different possibilities for the units, but these will be the standard units. Seconds for time, meters for position. Now the second section is called velocity. And, well, we need to start with a definition of velocity in one dimension. And the definition of velocity in one dimension is delta x divided by delta t. Now, throughout the course, we're going to be using delta notation. So here's the delta notation. Suppose we have some quantity which can vary. Then capital delta of Q means a change of that quantity. You have some initial value, Q initial, some final value, Q final. Q final minus Q initial is the change from the initial value to the final value. We'll denote that by delta Q. It's the change of Q. Delta is not a quantity itself. Delta is an operation. So we have delta, calculation of change, times operating on a quantity Q. So delta Q is one number. It's not two numbers multiplied together. Delta is an operator which operates on a variable. And delta Q is Q final minus Q initial. Now that's a change of the quantity. What I have here is delta x over delta t, but it's the lowercase delta. So another aspect of delta notation, delta Q, where I use the lowercase delta, means an infinitesimal change of Q. That is to say, delta Q is very small, whereas capital delta Q is just some change, some final value minus some initial value. It doesn't necessarily have to be small. But delta Q, when I use the lowercase delta, I imply that this is a small change. We might almost say an infinitesimal change. All I really mean is it's very small. If you use the ideas of calculus, it would be the limit delta Q tending to 0. But we don't use calculus in physics 231. So it's best if you just think of delta Q as something very small. Now, the average rate of change of the quantity Q over some time interval delta t, maybe I better blow this up a little bit. Oops. The average rate of change over a time interval delta t is capital delta Q over capital delta T. I have some interval of time. Maybe that's, 1 minute. And I have the change in this quantity Q during 1 minute. And then the ratio, delta Q over delta T, is the average rate of change during that 1 minute. We also define the instantaneous rate of change. And the instantaneous rate of change is little delta, delta Q over delta T. It's the change in Q over a tiny time interval. Suppose some object is changing, and I'm considering its rate of change over a period of about a minute. Well, the average rate of change would be the total change, delta Q over delta T with a capital delta. But at some time during that minute, if I want to know the instantaneous rate of change at that particular time, I take a very small time interval, let's say 1 microsecond. And I say, how much does Q change during that 1 microsecond? Then the ratio of delta Q over delta T for that 1 microsecond is the rate of change at that particular time. And when we define velocity, what we usually mean is the instantaneous velocity. That's delta x over delta t with a very small change in time and correspondingly a very small change in the coordinate. So that ratio will be the instantaneous velocity. Instantaneous velocity is suppose you're in your car, you're driving along a straight road. The instantaneous velocity is the velocity that's registered on the speedometer. But that's changing as you accelerate and decelerate. If you apply the brakes, your instantaneous velocity will decrease. If you press on the accelerator, your instantaneous velocity will increase. So this is the instantaneous velocity. Okay then. Velocity is the rate of change of position with respect to time. So we're always concerned with rate of change. And there are actually two kinds of rate of change. That we can define the average rate of change, which is delta Q over delta T, where delta T is not necessarily a small time, it's just some time interval over which Q is changing. And there's also the instantaneous rate of change. That's delta Q over delta T, where that's the infinitesimal change in time with the lowercase delta. So, for example, V is the position at t plus delta t minus the position of time t divided by delta t. It's the change in position as the particle moves from x at time t to x at time t plus delta t. The change in x is x of t plus delta t minus x of t. Now we divide that by the change in time, the time interval delta t. This small change in x divided by the small change in time gives me the instantaneous velocity v. Now, what are the units of velocity? Hey, Tommy, stop. Well, you see, we have here in the numerator meters and in the denominator seconds. So the ratio is meters per second. X is measured in meters, t is measured in time. So we have here meters per second. T is measured in seconds. So I have here meters divided by seconds, meters per second. So that'll be the standard unit for velocity. Or I should say, that's the unit we mostly use. Now, we could use other units. We could use miles per hour. If you're driving in your car on a straight road, you'll be observing the speedometer, which is presumably calibrated in miles per hour, or maybe kilometers per hour, not meters per second. So you'll have to be able to convert from miles per hour to meters per second. you'll have to know how many meters is 1 mile and how many seconds is 1 hour. And you'll have to convert from miles to meters and hours to seconds. Now, if the velocity is constant, if you're driving along your car and your speedometer says 30 miles per hour and it's not changing, then we can write x at time t is x0 plus vt, where x0 is the position of your coordinate position of your car at the time t equals 0, and as you're moving, your coordinate is changing by an amount vt in a time t. So this is the equation for position as a function of time, but that's only if v is constant. Say you're moving at 30 miles an hour. Well, then in 1 hour you'd move 30 miles. In a half an hour you'd move 15 miles. You'd move 30 miles per hour times the time in hours. But this equation is not true if the velocity is changing. Of course, it can't be true, because if the velocity is changing, then what would you put in for the velocity? It doesn't have a single value. It has a multitude of values. It's a variable quantity. So obviously this equation can't describe all situations. It's only when v is constant. Well, we define velocity as the rate of change of position. And now we define acceleration as the rate of change of velocity. So acceleration is equal to delta v over delta t. The change in velocity over a small time interval divided by the time interval gives me the instantaneous acceleration. That might be constant. In fact, I think in most of the problems, well, no, that's not true. In some problems, the acceleration is constant. And then we could use any time interval and the corresponding change in velocity. But for the instantaneous acceleration, it's the small change in velocity divided by the small time interval over which that change occurs. So in words, a is the rate of change of velocity with respect to time. Or if we put that into equations, a is v at t plus delta t minus v at t. That's the change in velocity from time t to time t plus delta t, divided by delta t. So it's the change in velocity, the final velocity minus the initial velocity, divided by the time interval or the change in time. Now again, what are the units of acceleration? Well, we have here a velocity divided by a time. The unit of velocity is meters per second. The unit of time is seconds. So what we have here is some number of meters per second divided by some number of seconds. We have meters per second per second. That's meters per second squared. So the unit of acceleration is meters per second squared. We could say meters per second per second. But if we treat that as a fraction, meters per second divided by seconds is meters divided by seconds squared. Now, kinematics with constant acceleration has a number of equations, and you'll be looking at those when you read chapter 2. So let me write down what are probably the three most important equations for kinematics with constant acceleration. First of all, v at a function of time is v0 plus a times t. Remember when we had constant velocity, then x as a function of time was x0, some initial value of x. So that's the coordinate at time 0, plus the velocity times time. That was valid for constant velocity. That's not valid here, because here the velocity is not constant. So don't use this equation when you have acceleration. But the point is, let me cross that out. The point is, when you have constant rate of change, then the quantity just increases as the rate of change times the time. Well, in this case, we have a constant rate of change of velocity. So the velocity increases as the rate of change times the time. And the rate of change of velocity is acceleration. So here's the equation for velocity as a function of time. And just as this equation was only valid when v was constant, this equation is only valid when a is constant. So this is an equation which you can use when you have constant acceleration. We won't always have constant acceleration, but with constant acceleration, we can say the velocity at time t is v0, which is some constant. It's the value of the velocity at time 0, plus at. That's the increase in velocity during the time t. Now what about position as a function of time? This would be the equation for position as a function of time if v were constant. But v is not constant. So now the position as a function of time has this form. It's x0 plus v0t plus 1/2 at squared. So x0 is the initial coordinate, the coordinate at time 0. v0 is the initial velocity, the velocity at time 0. And the increase in position is a combination of v0t plus 1/2 at squared. In other words, due to the acceleration, there's an increase in coordinate that goes like t squared. The fact that with acceleration the position changes as the square of the time was first observed and discovered by the great Galileo Galilei at the very beginnings of the scientific revolution. So Galileo really started the study of kinematics, the quantitative and mathematical description of motion. And that was one of his important discoveries. Suppose the initial velocity is 0, so the object starts with velocity 0. It starts from rest. Then its position increases as the square of the time. And the coefficient is 1/2 the acceleration. Now there's one other equation which is sometimes useful. Here I related x to t. Here I related v to t. I can write an equation which relates x to v. And the equation looks like this. V squared minus v0 squared is 2a x minus x0. And I'll leave that as an equation, as a calculation for you to prove. You know, here's v, here's x. Calculate v squared minus v0 squared. Calculate 2a x minus x0. Compare the two calculations. You'll find they're equal. So the square of the velocity increases linearly with the coordinate, or the coordinate increases as the square of the velocity. I could write it in terms of the delta notation. I could say delta v squared, that's v squared minus v0 squared, the change in v squared, is equal to 2a, a is a constant, so that's not changing, delta x. So that's a little more succinct way of writing this equation, but this is the equation you need to know. So memorize these three equations. Well, write them down in your notebook. I hope you're taking notes throughout this video, because you're going to need these equations when you come to do the homework problems. And write these three equations down in your notebook. In fact, memorize them so that you can write them down quickly when you take the test. Now, remember, they're only true if the acceleration is constant. And we will consider problems later in the semester where the acceleration is not constant. Then you can't use these equations. So don't think that this is the only set of equations you're going to need in Physics 231. This applies to some problems, and you have to know which problems does it apply to. Well, it applies when the acceleration is constant. Let's consider an example with constant acceleration. And the answer in the example is free fall in Earth's gravity. Let's set up a coordinate system. We'll call the coordinate for the vertical direction, we'll call that y. So here's the axis. Here's the line. And some object is moving either upward or downward in the vertical direction. We'll come to two-dimensional motion next week. It could be moving upward. That would be a positive velocity. It could be moving downward. That would be a negative velocity. The acceleration is downward. So the acceleration is negative. So the acceleration in the y direction is equal to negative a positive number, g. And the remarkable fact is that g is the same for every object. The acceleration due to gravity is the same for all objects. This was discovered by the great Galileo Galilei. You probably know the story of Galileo and the Leaning Tower of Pisa. Supposedly he dropped different objects off the Leaning Tower of Pisa, and he observed that they all fell at the same rate. In other words, they all had the same acceleration. So the acceleration, g, is the same for all masses. For all different massed objects, the acceleration is the same. It's g. And what's the value of g? G is 9.81 meters per second squared. Remember, our standard unit will be meters for distance, seconds for time. So the standard unit of acceleration would be meters per second, meters per second squared. And the acceleration of all objects on the surface of the Earth due to gravity is 9.81 meters per second squared. Actually, the value of g varies a little bit over the surface of the Earth, but not by very much. So we'll always, in this course, just take g to have the same value, 9.81 meters per second squared, everywhere. But if you measured g with great accuracy, you would find the acceleration due to gravity in Denver, Colorado, is not the same as the acceleration due to gravity in East Lansing, Michigan, for example. But it wouldn't be a very big difference. It was Galileo who showed that all objects fall at the same acceleration. Well, there can also be forces of air resistance, aerodynamic forces, which will affect how they fall. So, for example, which falls faster, a rock or a feather? Well, obviously a rock falls faster than a feather, but that's not because they have different accelerations due to gravity. Their accelerations due to gravity are exactly the same. It's because they have different air resistance forces. If you dropped a rock and a feather on the moon where there is no air, you would find the rock and the feather fell at the same rate. Because on the moon there is no air resistance. There's no aerodynamic forces, just the gravitational force. And their gravitational accelerations would be the same on the moon, just as the gravitational accelerations are the same on the Earth. And so they would fall and hit the surface of the moon at exactly the same time. Well, if you took two objects that don't have a very big effect of aerodynamic forces, like a cannonball and a musket ball, supposedly Galileo went to the top of the Leaning Tower of Pisa and he dropped a cannonball and a musket ball. They're both accelerating down because of gravity, and there's not much effective air resistance on either one. Now, what he observed was they hit the ground at the same time. Now, Isaac Newton, who lived after Galileo a little bit, Isaac Newton explained why. Why is the acceleration due to gravity the same for the cannonball and the musket ball? They have much different masses. They have much different sizes. The cannonball is much more massive than the musket ball. So why should they have the same acceleration? And Newton showed acceleration is force divided by mass. That's one of Newton's laws of motion. And the force of gravity is the mass times gm over r squared, where g is a universal constant, m is the mass of the Earth, and r is the radius of the Earth. That's Newton's theory of gravity. And if you combine Newton's theory of acceleration, acceleration is force divided by mass, and Newton's theory of gravity, force of gravity is mass divided by gm over r squared, you see the acceleration, the mass cancels out. You have mass times gm over r squared, that's force, divided by mass. Well, mass divided by mass, the masses cancel. So the acceleration is gm over r squared. For any object, it doesn't depend on the mass of the object. And that's the 9.81 meters per second squared of Galileo's constant acceleration. So Galileo discovered that acceleration is the same for all masses at the surface of the Earth. And Newton explained why and went beyond. He explained what is 9.81 meters per second squared. What's so special about that number? Well, it's a universal constant, g, times the mass of the Earth divided by the radius of the Earth. It's really the distance from the falling object to the center of the Earth. But if the object is near the surface of the Earth, that's just the radius of the Earth. Which falls faster, a hammer or a nail? Well, we'll finish up this introduction to Chapter 2 with an example problem. Throw a baseball straight up. Calculate the coordinate y as a function of time. And let's suppose that the initial height is 1 meter, which is about waist high if you're pretty tall. So you throw it up from waist high, and let's say the initial speed is 10 meters per second. That's pretty fast. So you have to throw a baseball up from a height of 1 meter, waist height, at initial speed 10 meters per second. Then what's the coordinate as a function of time? Well, remember, for constant acceleration, the general equation, x is x0 plus v0t plus 1/2 at squared. You wrote that down in your notebook, didn't you? I told you to memorize it. Now, for this problem, the coordinate is y, and y is vertical. So y is measured upward from the surface of the Earth. So the initial height will be y0. That's 1 meter. The initial velocity is 10 meters per second, and it's upward, so it'll be positive 10 meters per second. And the contribution from acceleration will be minus 1/2 gt squared. Because the ball, as it's moving upward, it's accelerating downward. It's always accelerating downward with the same acceleration g. So at this point, I'm plotting here height versus time. So at this point, the height is 4 meters. The time is half a second. It's moving upward. The slope, the rate of change of the coordinate as a function of time is the slope of the curve. Slope of this curve is positive. So it's moving upward. Well, you can see it's moving upward. This is the height. The height is increasing until it reaches a maximum, and then it starts decreasing. So the ball starts at y equals 1. It goes up. Then it comes back down and hits the ground. Here's the ground. Here's 1 meter. That's the initial height. Well, we'll call that y0. At this point, the ball is accelerating downward. It's moving upward, but it's accelerating downward. At this point, the ball is accelerating downward. It's moving downward. It's always accelerating downward. When it's moving up, when it's moving up, it's accelerating downward. Don't confuse velocity and acceleration. Velocity can be positive or negative. Upward is positive, downward is negative. Acceleration, well, in general, it could be positive or negative, but near the surface of the Earth, the acceleration due to gravity is always negative because it's down towards the center of the Earth. So here's the maximum height. Here's the maximum height, y max. You can see from the graph, y max is, about 6 meters. All right, so that's the equation. Let's check some numbers. Y at an arbitrary time t is 1 plus 10t minus 0.5 times 9.81 t squared, where we're using the units of seconds for time and meters for height. So let's take 1 second. It'd be 1 plus 10 times 1 is 10, minus 0.5 times 4.91 times 1 is a half of 4.91 is 9.81 is 4.905. So it'll be 6.095 after 1 second. So after 1 second, it's more or less at the maximum. It's a little bit, it's around 6 meters. How about at 2 seconds? Well, it'd be 1 plus 10 times 2, so 1 plus 20, minus 1/2, 9.81, 2 squared. 2 squared is 4, divided by 2 is 2. 2 times 9.81, what's about 20? Let's say 19.62. So I have here 21 minus 20, it's about 1. A little more accurately, it's 1.38 meters. So at 2 seconds, that's here. It's back down to about waist height. It's a little bit above waist height. It started here at I don't know if I plotted this starting from 1. It looks like I started this with y0 equals 0, so the graph is not quite accurate. But anyway, this really should be the initial height, 1. It went up 6 meters above the initial height. It came back down. It reaches the ground after about 2 seconds. It reaches the maximum height after about 1 second. All right, so there'll be problems very similar to this on the Lon Kappa homework assignment. So if you understand this calculation, you'll be using it again. Now, this video has been an introduction to Chapter 2, but only an introduction. You haven't learned everything from watching this video. It's very important to read the chapter. So read Chapter 2. Take notes. You know, when you read the chapter, take notes. You should have a physics notebook for this semester. And as you read each chapter, make about 1 page of notes for each chapter. You're going to need those notes when you take the exam and when you do the homework problems. Otherwise, you'll have to go back and look things up in the book, which is very time-consuming. So be sure to take notes. Then do the homework problems, which are on lonkappa.msu.edu. They're in 2 sections, or two folders. One folder is called the first questions for Chapter 2. So I guess that's called the first questions number 1. It's a small number of multiple choice questions. After you've read the book, you should be able to answer the first questions. It shouldn't take very long, maybe half an hour, probably less than half an hour. Then you have the problem set, which is called problem set 1. That'll take more than a half an hour. That'll take multiple hours. I don't know how many problems there are, maybe 15 problems. Say each problem takes a half an hour, that would be 7.5 hours. It may not take that long. Some people have taken physics in high school, and this topic of constant acceleration is very common to courses on physics in high school. So some people can probably do these problems more quickly. But anyway, leave yourself plenty of time to do the homework. Don't try to do the homework all at the last minute, because you won't be able to finish all the problems. You won't get all the points. So, do the homework over a period of several days. Do 1/3 of the problems one day, another 1/3 the next day, the final 1/3 the final day. There are hints for the homework problems, and there will be a Zoom meeting which will provide hints for some of the problems.